Hi, this is Mr. Heineman from Evergreen High School, and this is for my Algebra 1 classes. This is Standard 2.1, Solving Equations and Inequalities. So when it comes to Unit 2 and Standard 2.1, it's all about solving, and when we're talking solving, we're using what are known as the properties of equality. There are 4 of those that relate to all 4 of the operations in math: addition, subtraction, multiplication, and division. And what the properties of equality mean is that you always must do the same thing to both sides of an equation. So when we look at the equal sign, that's kind of a dividing mark, and on each side of that we always do the same thing, and it has to be exactly the same thing, the same operation with the same term. And like I said, we use these to solve equations for variables, and that's what we're doing here in Unit 2 and on Standard 2.1. So when it comes to the properties of equality, and we're using them with equal signs and equations. So we think of the equal sign as like a divider. And when we say sides, that's what we mean is each side of the equal sign. So if I add 3 to both sides of the equation, I show that by writing it on each side of the equation underneath. And then I add 3. So because x and 3 are not like terms, I can't combine them into a single term. I have to write x plus 3. And then on the other side of the equal sign, though, 6 plus 3 is 9, so I can write 9. And so my new equation is x plus 3 equals 9. And that has the same solution. X is the same value still. It's still 6. It's just written in a different form. If I subtract 3 from both sides, and I don't always have to write the dividing sign or dividing line, I can just write the 2 subtract 3's on each side. That means I'm subtracting 3 from both sides. So x minus 3 equals 3, because 6 minus 3 is 3. X is still 6, but it's just written again in a different way. So if I multiply, usually when I multiply, I will put x in parentheses and I'll multiply out here. And I can show that over here as well. So 3 times x, well, that's 3x. 6 times 3 is 18. So x is still 6. It doesn't change the value of x, it just changes what the equation looks like. Same thing here. If I divide by 3, I still have to write x divided by 3 because I can't do much with that. And then 6 divided by 3 is 2. So the properties of equality have to be done to both sides of an equation. And we use the equal sign as the dividing mark. So when we say both sides, it's both sides of the equal sign. That way the value of x doesn't change whenever I do any properties of equality. And the equation doesn't change either. It has the same solution no matter what. So when it comes to solving equations, the solution to an equation is the value of the variable that makes the equation true. So whatever value the variable takes on that will make the equation true is a solution to an equation. So solving an equation is using mathematical properties to transform an equation so that the variable is alone on one side. And so we have a final equation that reveals what the solution is. And it always ends with the variable alone. Usually that's x, and so it would be x equals some number, and we don't always know what number that is. So now we're going to try our hand at actually solving some equations. So the first thing we should be able to do when it comes to solving equations is to verify whether something's a solution. And a solution, remember, is a value that makes an equation true. So if I'm going to verify which one of these is a possible or is the solution to this equation, I simply replace or substitute that value for x in that equation. So let's try -4 first. And then I just work out the math. So I got 6 times -4 is -24. Remembering my order of operations. On the other side, 2 times -4 is -8. So then -24 minus 3, well, that's kind of like adding these two negative numbers. So -24 plus -3, because they're both negative and I'm adding them, I can add the two numbers for 27 and just make it negative. On the other side of the equal sign, 13 plus -8, well, I can ignore this plus sign and really treat it just like 13 minus 8, which is 5. -27 is not equal to 5. Therefore, this must not be the solution. Now, I'm not sure if 4 is the solution or if we're just being tricked here, but we'll check it just to make sure. So we'll plug 4 in to the equation to see if that is correct. So 6 times 4 is 24. And 2 times 4 is 8. 24 minus 3 is 21. 13 plus 8 is also 21. That checks out. So x equals 4 must be our solution because that's the value that made the equation true. So when it comes to solving, we use the properties of equality to solve. And the way we do that is we look at what is happening on the side of the equation with the variable, and we do the opposite operation. So if we have x minus 3 equals 3, we're going to do the opposite operation, which is addition, and we're adding the same value. And remember, the properties of equality say we have to add to both sides of that equal sign. So when I add -3 and +3, those cancel out, and that leaves x all by itself on the left. 3 plus 3 is 6. So the value that makes this equation true is x equals 6, because 6 minus 3 equals 3. So we use the properties of equality to solve equations. So if it's plus x plus 4, we're going to subtract 4 from both sides again. And that leaves x equals 6 one more time. Kind of guess where this is going. When I have division, I multiply by that value to get rid of, and that cancels the multiplication, x, or the division I should say, and x is 6. And then when it's multiplication, the opposite is division. So we divide both sides by 4. X equals 6 again. So we just use the appropriate property of equality to solve these one-step equations. When it comes to solving two-step equations, which is where we have more than two operations related to x here, what we do is we can think about what's happening. And we're thinking about it in terms of what's happening to x. What's happening to x first is we're multiplying by 4. Then after that, we're adding by 7. Okay, and we know that's right because if we did the order of operations, we would plug in a number for x, multiply by 4, then add 7. And whatever that is, whatever value x is, it ends up being 35 after I've done those two things. So to solve, my solving plan, and again, I'm planning this out before I start, not just jumping right into it. My solving plan is going to be to do the opposite operations like I said in the previous problem, using the properties of equality, but we're going to not just do the opposite operations, we have to do them in the opposite order, which means if I added 7 second, I'm going to subtract by 7 first in my solving plan, and then I undo the multiplication, which is division. And when I finish, I should end up with x by itself. So we're going to start by subtracting 7 from both sides. And again, I make sure I'm on both sides of the equal sign. So 4x is left over here because the 7's cancel. 35 minus 7 turns out to be 28. And now that I have a one-step equation, I use that one step, which was the second step I said I would do, divide by 4. The 4's cancel. X equals 28 divided by 4, which is 7. So in a two-step equation, I always think about what's happening to x, what happens first and second, and then I reverse, or I undo those in the reverse order. So I would do the opposite operations in the opposite order, and that way I will get x by itself, and then whatever number is on the right or on the other side of the equal sign, depending on where x is, then that's my solution. So sometimes I have to do multi-step equations where I have to include some other steps that aren't always the properties of equality when I'm doing my solving. For instance, here we have this problem where we have it's a distributed property. I need to distribute the 2 first before I can start solving. So I go ahead and distribute the 2, and because distribution is not a property of equality, it's not done to both sides. It's just done to the one side because it's just rewriting this in a different form that we can actually use, because now we have it set up as a two-step equation. I add 14 to undo the minus 14. Oops, and then I wrote the wrong number. It's actually 16. And then I divide by 2 because that's going to give me x by itself. X equals 8 in this case. Sometimes we have variables on both sides. And one thing to know is that the properties of equality work with any terms. They don't just have to be numbers. They can be any terms on either side of the equation. So what we're going to have to do is we only want x's on one side because we're going to solve for x by getting x alone on one side of the equation or the other. So I'm going to need to get rid of x either on the left or on the right. And I personally choose by trying to keep the coefficient of x positive. So whatever's in front of x, I'm going to look at the 2 and I'm going to say, well, if I subtract 6x from both sides, that will get rid of the x over here, and then this will still be a positive coefficient for x. So when I do that, I leave 34, and then I have 6 plus a 4x. 10 minus 6 is 4. And then I do the rest of my solving. Subtract 6, 28 equals 4x, and then divide by 4, and I'm running out of a little room here, but I can write over here 7 equals x. And so the value of x is 7. That's the solution. I just had to remove x's from both sides of the equation, or from one side of the equation, because they were on both sides. And I always want to be aware of that when I am solving and doing all the extra steps that I need to do that will help me solve. And when it comes to these ones that have x on both sides, I always deal with x first, because then it ends up that my equation is a two-step equation that I know how to solve. Alright, so let's do one more example of solving multi-step equations. And this one's got a few more steps. Let's start with our distributive property because I see it, and that will help get me set up for the next set of steps. So again, I've got x's on both sides, and again, my personal preference is to get rid of x's on the side that will allow me to keep the coefficient of x positive. So I chose to subtract 5x because that will, 6x minus 5x is just x. And this is actually a little bit easier than I thought it might be, because now all I have to do is add 8. It turns into a one-step equation. I just got to remember that negative 6 plus 8 is really like 8 minus 6. It's just 2. So when it comes to multi-step equations, we're focusing in on, are there things that I need to do to transform one side first? Then, do I need to get rid of x on either side? Then, once I've got gotten rid of x on one side, or if I didn't need to, then I go ahead and do the rest of my steps like I would normally. So solving inequalities is really similar to solving equations. A solution, of course, is a value that makes the inequality true. So then solving an inequality means using math properties to transform an inequality so that the variable is all by itself on one side. So it's the same process as equations, but there's one small difference that we'll get to when we actually get into solving. So we start solving by verifying solutions, just like we did with equations. The difference, of course, is that an equation had a single solution that was correct, and inequalities, because they use things like less than and greater than, can result in more than one solution being correct. So it could be that both 6 and 4 are solutions. We just don't know until we try. So in either case, we're going to substitute the value into the inequality for x and then check to see is it correct. So in this case, 5 plus 12 is exactly 17, but since our inequality symbol is less than, 17 is not less than 17. So this is no, that's not a solution. No solution here. Whereas if we try 4, five plus 8 is 13, which is less than 17. So that checks out. So 4 is a solution because it made the inequality true. 6 is not a solution because it didn't make the inequality true. Even though it could have multiple solutions, in this case, it only had one solution among the 2 that were available. So as I said, solving equations, solving inequalities are basically the same. In this case, we would look at this side of the inequality, and we see that x is being multiplied by 2, and then we're adding 5. So to solve this inequality, I'm going to first subtract 5 because that was the second thing that happened. And the inequality symbol needs to stay there. So when we talk about both sides of an inequality, we're talking of the inequality symbol. So subtracting 5, the whole point was to get rid of that 5, which we did. Leaves 2x over here. And then 17 minus 5 is 12. So now I divide by 2, and x is less than 6. So x could be any value less than 6, and that would qualify as a solution. So that could be, that's an infinite number of solutions, anything less than 6. So we're going to keep that in mind when we talk about graphing solutions a little bit later. But solving inequalities is basically the same as solving by equations, but there's one difference. And that difference is when we divide by negatives. Because when we divide by negatives, the inequality symbol is affected by that. So when we look at this equation, or this inequality I should say, and we're going to solve it, we're still doing the same steps. So we see x is being multiplied by negative 5, and then we're adding 2. So we have to start with subtracting 2. To to get the inequality a little bit simpler before we can actually solve it. But when we divide by a negative value, that causes this inequality symbol to flip. And so I flip the inequality symbol when I multiply or divide by a negative number. And when I divide 25 by negative 5, I get negative 5. So now instead of x greater than or equal to, it's x less than or equal to negative 5. And so, because what happens is like the solutions kind of flip from what we think they would be. And that's because this will flip everything when we put a solution in here and multiply. So multiplying or dividing by a negative number will result in a flip of the inequality symbol when you're solving inequalities. So again, multi-step inequalities, just like multi-step equations, I'm going to try and do things to make it simpler and make it easier for us to solve on both sides. So I look and I see this distributive property. We're going to have to do that first. Okay. The only other thing we're going to watch out for in, I'm going to put 5, that's 3x, in inequalities is that dividing by negatives, and remembering that when we divide by a negative, it's going to cause the inequality symbol to flip. All right, so here we can combine the two like terms, and I'm not going to rearrange these. I'm just going to say, you know, I know I can rearrange them and combine them. So I know 6x minus 3x, I know that's 3x, and then my plus 2 is still there. Okay, and I don't know why I put an equal to there. That's not an equal to. Okay, so now I'm going to go ahead and solve. And knowing that we would be dividing by negatives, that dividing by negatives causes a flip of the inequality symbol, I'm going to try to avoid that as much as I can. So in this case, I'm going to subtract 2x from both sides, because that way I hope anyway, I will keep my x coefficient positive, and I did. Okay, because I know I need to put x's just on one side. Now I can just solve this by subtracting 2, and x is greater than 8. So x is greater than 8. That's a lot of possibilities, but I made sure that I followed my properties. I did the distributive property first. I know I used commutative and associative properties to rearrange and group like terms together so I could combine them, and then used properties of equality to solve, starting with x's and then numbers so that I could get x by itself. Okay. So an additional thing that we do with inequalities and equations for that matter is we will graph solutions on a number line down here. So we're going to solve this inequality and then graph the solution down here on this number line. So I'm going to do my normal solving, subtract 2 from both sides, negative 4x greater than or equal to 20. And then of course, when I divide by negative 4, so that's my next step, I'm going to make sure that I flip the inequality symbol. So now x, instead of being greater than or equal to, is less than or equal to negative 5. And on this number line, I'm going to find negative 5, and I'm going to put a circle there. And then I'm going to look and say, okay, so if this were just a straight less than and not equal to, I would leave that open. But because this has an equal to, I'm going to fill in that dot. And so that way I have a filled in circle to say, yes, one of my solutions is actually negative 5. And then I'm going to draw an arrow in the direction of the inequality symbol. So with this being less than, on the number line, less than means we go to the left, and we can make that darker, I had maybe a ruler, I could draw it straighter, but I make sure that it's clear that my solutions are going to be all the point -5 and then anything less than that. Okay. When it comes to graphing solutions of equations, well, I just do normal solution stuff. Let's distribute first. And then I'm going to solve for x. In this case, I'm going to subtract 3x first. Get x's on the right-hand side. I'll add 2, add 2. 4 equals 2x. If I divide by 2, I'm going to put it over here, x equals 2. So in the case of x equals 2, I'm going to put my circle at 2, and I'm just going to put a circle because this is an equation. It only requires a dot at the solution, and we know there's only one solution. With inequalities, there are infinitely many solutions, and that means that because there are infinite solutions, I'm showing an arrow one way or the other showing where those solutions are on the number line. So speaking of numbers of solutions, inequalities, as we know, can have infinitely many solutions. An equation only has one solution, but there's also the possibility that any real number could be a solution of either an equation or an inequality. And when we solve, we first, of course, do all of our solving steps. So in this case, we have a couple of distributive properties to take care of. Make sure that -3 goes with it when we multiply. Same thing here. That the -3 goes through the whole thing. Oops, no x though. And then I can rearrange combine like terms. 7x minus 3x, that's 4x minus 12. And then -18 minus 15, that's like adding 2 negatives. That's -33. And then -3x plus 7x is plus 4x. So now I'm going to get x's on one side or the other, and I'm going to subtract 4x to do that. Subtract 4x. And I look and I go, well, subtracting 4x is going to cancel those, but it's also going to cancel those and leave just -12 is greater than -33. And the reality is that -12 is always greater than -33. Since that is always true, it doesn't matter what numbers we would put in for x. All real numbers would work. So the solution would be all real numbers. Okay. In an equation, if we ended up with the same thing on each side of an equation, then we would say all real numbers also. If this was not true, whether it was an equation or an inequality, we would say there is no solution because there's no value we could plug in for x that would make the inequality or the equation true. It's just not possible. If this were a normal inequality and we solved it and we got a normal x is greater than or less than or whatever, that would be infinite solutions, which is different than all real numbers because it is a specific set of solutions. It's still infinite like the real numbers, but I couldn't just put anything in. Whereas all real numbers means I can put any number I want in and it doesn't matter, it will work. And then no solution, of course, means there's no possibilities. There are no numbers I can put in that would work. So the last thing that we need to be able to do is rearrange formulas. We can always solve for any variable in a formula. It's just a matter of what does the resulting formula look like. And we have to make sure we follow the order in which we did operations because we're still going to have to eventually undo that order. So when I look at working from x, I'm going to make a small list up here somewhere. So maybe right here. So the first thing that happens is we multiply by 3. This is all what's happening to x. Then we subtract by 9. Then we have a divide by a variable b. And it doesn't matter that it's a variable. It just matters that we know what operation it is, so we can undo the operation when it comes time to solve. So when it comes time to solve, we're going to work backwards, and we're going to undo this one first, and then we're going to undo this one second, and then we're going to undo this one last, because we did them in the reverse order to get this expression. So we're going to multiply by b, and we're going to multiply both sides by b. And the thing is, when I have just a bunch of variables, I just list them. Usually I like to list them in alphabetical order, but the whole point of multiplying by b was to cancel out that division by b, and now I have 3x minus 9. And now I can undo the second step, which is to add 9. And again, when I add 9 over here, because 9 is not a like term for btz, I'm just going to write btz plus 9. So I can't combine them. And then I have 3x. And then the last thing I'm going to do is I'm going to divide by 3. And that will allow me to get x by itself. So now I just have this expression btz plus 9, all of it divided by 3. And that's what equals x. And I've solved this formula for x. I know there's no solution, there's no value for x, but that doesn't mean we didn't solve. And I could solve it for any variable I want. I just might have to do some extra work, depending on what it is. So really, that's why we say solve. And the act of solve means to get the desired variable by itself. And that's really what solving is all about. It's not about finding values, because sometimes we don't find values. There are plenty of formulas that we solve for variables that the result is, instead of being a value, it's another expression in variables. And then we can plug values into those variables and use that to find something. So that's it for Unit 2. Good luck.